We have a couple of questions here, but the first one is asking us if we have 60 samples, okay, and there's a size of each of them being 25 each, what does the distribution of the population, um, what does the distribution look like? Okay, so what this means is that we're taking 25 um, like a sample of, let's say, there's 25 of them in the sample and there's 60 samples. So because 60 is like quite a lot, we're taking quite a lot, as we do that, eventually, we might start off with, if we take only a few, it might look like this, but then as we take more and more, it begins to resemble more and more of a bell curve. All right, and then eventually it just looks exactly like a bell curve. So it'll look pretty good. The steps are quite small, okay? And what we can say is that the mean here, all right, the mean will be there. So this is saying that the distribution will occur at around, it'll basically look like a bell curve. And so that's the important takeaway of this question. So for part A, the next is asking, does this particular equation here, all right, represent a probability density function? So I'm going to draw it down the bottom here. And what we're going to say is that we have some function called f of x, and that's equal to a piecewise thing where part of it is equal to x to the power of 3. Otherwise, it's 0. And this is only for this value here. Okay, so first of all, is it a probability density function? What needs to happen is that there cannot be any negative number. So at any point, f of x cannot be less than 0. And then also, the sum of all values must be equal to 1. Okay, so let's plot this thing to get a good understanding of it. So we've got our axis here. We start off at 0, okay, and then if we say f of 0 is equal to 0 to the power of 3, and that is just equal to 0. But what about f of 1? Well, that's equal to x to the power of, 1 to the power of 3, which is equal to 1. Okay, and so what we can say is normally the curve looks like that if it's a cubic. So in this case, it'll go up and around and kind of look like this. Okay, so in this case, it's we're just trying to check, like, does this value here, does the area under the curve equal to 1? And so when we find the integral from minus infinity to positive infinity, basically all of the areas other than from 0 to 1 will be equal to 0. So we can split this up to say that it's actually equal to, I'll give myself a little bit more space, it's actually equal to minus infinity to 0 for 0, right? And then plus 0 to 1 for x to the 3, and then plus 1 to infinity for 0. And so that means that we can just scratch those two and focus in on the middle one. So finding the integral, assuming you're all pretty good with that now, it's going to be equal to this from 0 to 1. Okay, and so we substitute in the 1 at the top and then minus it by the 0. So it's 1 to the power of 4 minus by 0 to the power of 4. All of that stuff is equal to 0. And so what we're left with is 1/4. And that means that the area under the curve isn't equal to 100%. All right, it isn't equal to 100%. This area underneath here is only equal to 0.25. So what happened to the other 75% of the probability? And that's why it's not considered. So f of x is not a probability density function. Cool. The next bit, part C, explain why the means of many samples is a good approximation of the mean. So what happens is, if we have a sample of a population, right? And we've got a population, so we've got a box, and we've got the red and the blues. Now, if we just start drawing circles in here, eventually what we'll find is that if we keep drawing circles, we're more likely to find that the same area of the left of the red one and the blue one exists. So it's a good approximation because the sample mean, I'm going to call this x, is an estimator. All right, it estimates the population mean. And I'm going to call that mu. So this weird looking u thing. Okay, and so what we expect is that the approximate value, or the expected value of x, should be equal to mu. And as we increase the number of circles, as the samples increase, so as the samples increase, the average of the means, okay, the average will converge to mu. So there's this thing called regression to the mean. And so as you take more and more samples, you're more likely to get, like, the average of it is more likely to be the mean. Okay, so that's part C. Let's go on to part D. Okay, and this one is asking us, explain why the sampling distribution of the sample means has a very small standard deviation. So let's go back to our box. Okay, we're going to use some maths here, but just so you can wrap your hand around it. If we've got like lots of different colors here that represent the two possible fractions here, and we start taking circles of them, right? And we just keep doing that over and over again, and they can be really weird ones, right? All possible traces. What we're going to say is that eventually, as we add them up, they are going to be their like standard deviation is going to reduce. So explain why the sampling distribution has a very small standard deviation. And that's because we've got our formula sheet to say this occurs. Okay, so we use this formula, that's going to be 1 mark. So, and we say, as the sample size increases, our sample, which is usually denoted by x, the standard deviation of our sample decreases. So if we take like a bigger circle here, we're more likely to represent the actual value of the mean, which is this value here. So 1 mark by writing this equation. Another mark is going to occur by saying, as n increases, the sample standard deviation decreases. Okay. That's there we go. That's the solution to part D. But now we go on to part E, and it says gives me 3 types of bias that can occur. All right. You've got sampling bias. Okay. And this occurs the method when the method um, doesn't represent the population. So the method of sampling doesn't represent uh, the population. Okay. An example of this might be surveying people at school, right? If you only uh, ask for people's opinions in one spot of the school, some people might not go there. So you're not going to get a representation of the entire school. So you have to change where you might be asking people your questions. So instead of only asking it in one particular classroom, you're only going to get that class right. You're going to have to ask in different areas. The next one that we've got is response bias. Okay, so we can um, yeah, we can like ask leading questions, or we can um, ask like people can want to do good instead, and so that will give them a different question, a different response than what they actually believe. The third one is like the non-response bias, where people don't respond to the sample themselves or the questionnaire themselves. So you can say like non-response bias. Non-response bias. Okay. And so there you go. That is the answer to all of those questions. There's plenty of exam questions like this on my website if you want to get better and practice the questions that are likely to appear in your exam. So jump to the description and find all of them there with solutions and hints as well as videos.